Okay, let's unpack this. We're diving into something that's, well, usually hidden away in the basement or a closet. Forced air heating. Every time you touch that thermostat, you're actually kicking off this whole sequence, a pretty complex chain of the electrical events.
It really is. People feel the warmth, they feel the air moving, but the underlying controls, that electrical side,
Yeah.
it's surprisingly sophisticated.
Yeah, and that's our mission today, isn't it? We're kind of cracking open the technical manuals, the stuff electricians use, to give everyone a shortcut to understanding how these things actually work, both gas and electric.
Exactly. We'll look at how they function, the layers of safety built in, and how they achieve modern efficiency levels.
Because it really does matter whether you're dealing with a simple home furnace or some massive commercial unit. Understanding the control voltage is at 120 volts, 24, or even those tiny millivolts. And the safety cycle, that's key.
Knowing the sequence of operation is crucial.
Right, identifying the parts and how they talk to each other. Okay, so where do we start? The absolute basics.
Let's start simple. Pure electric heat. Think of a space heater, or even a full electric furnace. It all comes down to the Joule effect.
Resistance heating.
That's it. You force electrical current through something that resists it, a wire, usually nichrome or tungsten, and that resistance creates heat. Simple physics.
Add a fan to blow the heat out, maybe a reflector in a small unit.
And that's basically it. An electric furnace is just a much larger version of that. Lots of heating elements, a powerful fan connected to ducts, but importantly, no combustion.
Okay, so things get more complicated when you add gas.
Definitely. Now, you still find 120-volt systems, especially in commercial or industrial settings, workshops, garages, places like that.
And the big difference there is the control voltage, right? It's running at the full 120 volts.
Correct, which means you don't need that step-down transformer, that 24-volt circuit, just for the gas controls. It simplifies that aspect a bit.
But these units pack a punch, heat-wise. So I saw something in the notes about a special valve, a step-open gas valve.
Ah, yes. That's an important safety feature for those higher output units.
Why not just open the valve fully? Why the steps?
It's about managing the ignition.
Hmm.
Think about it. A big rush of gas igniting all at once can be quite forceful. An explosion, really, inside the heat exchanger.
So the step valve softens that.
Exactly. It opens partially first, allows a smaller amount of gas for a smoother, less intense initial ignition. Then, a few seconds later, it opens fully. It just reduces the mechanical stress. A safety buffer.
Makes sense. And the wiring is pretty robust. 2 parallel circuits at 120 volts.
Yep. One circuit is basically the fan control switch and the motor. The other is the heating control, thermostat, high limit switch, all in series with that main gas valve.
Yep.
Straightforward power control.
Okay. Now let's shift gears to what most homeowners probably have. The standard residential gas furnace, the ones running on 24 volts.
Right. The low voltage control circuit, fed by a small Class 2 transformer, much more common in homes.
And if we look at the older ones, the ones with a standing pilot light, there's that fascinating little safety device, the thermocouple.
Oh, the thermocouple is ingenious. Truly, it's completely self-powered. The heat from the pilot flame itself generates a tiny DC voltage.
How tiny are we talking?
Really tiny, like 26 to 32 millivolts. That's thousandths of a volt. Open circuit, anyway.
Wow. Can that actually do anything? Can it open the gas valve?
No, and that's the clever part. It doesn't have nearly enough power to pull the valve's armature open against its spring.
Ah.
It only has enough power to hold the armature in place after you've manually pushed it in.
So that's why you have to hold down that reset button when you light a pilot. You're physically holding the valve open.
Until the thermocouple gets hot enough from the pilot flame to generate those few millivolts. Then it can take over holding the armature. Let go too soon, and pop, it shuts off.
That is elegant and completely fail-safe, right?
Right.
Pilot goes out, voltage drops.
Instantly, the armature releases, the spring snaps the valve shut, cuts off gas to both the pilot and the main burner.
Yeah.
100% shut off. Brilliant low-tech safety.
Now, staying with gas valves for a moment, there are different types, but one seems dominant now.
Yeah, historically you had separate safety valves, solenoid valves, diaphragm valves. But today, you mostly see the combination gas valve.
Everything rolled into one.
Pretty much. It integrates the pressure regulator, the main safety shutoff mechanism, the part that works with the pilot system if it has one, the main valve itself, and usually a manual shutoff knob. It just simplifies installation and manufacturing.
Okay, good to know. Before we leave these standard furnaces, the fan and limit switch. Getting those settings wrong causes problems, I hear.
Oh, big time. This controls when the main blower fan turns on and off. It dictates comfort, efficiency, and noise. if it's wrong.
So there's a high limit setting. That's pure safety, right?
Absolutely.
Yeah.
Usually around 82 to 93 Celsius. If the furnace gets hotter than that, something's wrong, and it shuts the whole thing down. Critical safety backup.
Then the fan on setting.
When the blower starts.
Right, typically 49 to 60 Celsius. You wait for the furnace heat exchanger to get reasonably hot before you start blowing air across it. Otherwise, you get a blast of cool air first.
Yeah, fan off. Usually 32 to 38 Celsius. Keeps the fan running after the burner shuts off to scavenge that leftover heat from the exchanger. Don't want to waste it.
But the gap between on-end and OFF, that's crucial.
Hugely. That temperature differential. If it's too narrow, say, the fan comes on at 50 and shuts off at 45, you get fan cycling.
What's that like?
It's maddening. The fan turns on, cools the chamber just enough to hit the OFF point, shuts off, but the residual heat immediately pushes the temp back up, so it turns right back on again. On, off, on, off.
Sounds awful. So you need a decent gap.
Yeah, the recommendation is usually a 17 to 22 degrees Celsius difference between the fan on and fan off settings. Prevents that rapid cycling.
Okay, let's make the leap now. High efficiency furnaces. Condensing furnaces. We're talking big jumps in AFUE ratings, right? From maybe 78% up to 90, 95, even 98%.
Exactly. Energy Star territory.
And it's achieved through, well, kind of counterintuitive engineering.
How so?
Standard furnaces need to get their exhaust gases out fast and hot, keep them above the dew point so water vapor doesn't condense inside the furnace or flue.
High-efficiency furnaces do the exact opposite. They deliberately cool the exhaust gases way down, forcing that water vapor to condense inside the furnace.
Why? Just to grab every last bit of heat.
Precisely. Latent heat of vaporization. There's a significant amount of energy released when water vapor turns back into liquid water. They capture that heat.
But wait, condensation inside a furnace. And exhaust gases have CO2. Doesn't that create profit?
It creates carbonic acid. Yes.
Yeah.
Water plus carbon dioxide.
Oh.
It's corrosive.
Acid. Inside the furnace, how does that not destroy it?
That's where the secondary heat exchanger comes in. This is the key component unique to condensing furnaces.
Okay.
It's specifically designed to handle this cooling and condensation process. And crucially, it must be made of stainless steel or some other highly corrosion-resistant material. Regular steel wouldn't last long at all.
So that's a major design difference. Primary heat exchanger does the main work. Secondary squeezes out the rest and deals with the acid.
You got it. And because the exhaust leaving that secondary exchanger is so cool, often under 40 degrees Celsius.
Wow, that is cool for exhaust.
It is cool enough that you don't need a traditional chimney. You can vent it using plastic PVC pipe. Schedule 40, usually. Often right out the sidewall of the house.
Ah, that explains those white plastic pipes you see on newer homes.
That's the exhaust.
Yeah.
And, critically, these furnaces must have a condensate drain line installed properly.
To get rid of the carbonic acid.
Yes. If that drain plugs up or isn't sloped correctly, the acid backs up, pools inside the furnace cabinet, and starts eating away at everything else. It's the Achilles heel, really, the price of that super high efficiency.
Okay, so efficiency comes with complexity. Let's talk controls for these modern units. The standing pilot is long gone, right?
Oh, yeah. Replaced by electronic ignition systems.
Yeah.
Much more reliable and saves gas.
What are the main types?
Two main ones. First is the hot surface igniter, or HSI. It's a small ceramic element, usually silicon carbide or silicon nitride.
Ceramic.
Yep. It heats up incredibly hot when electricity passes through it, like 1,370 degrees Celsius. Red hot. It sits right in the gas stream and ignites it directly.
Any handling precautions for those?
Big one. Never touch the ceramic part with your bare fingers. The oils from your skin create hot spots when it heats up and cause it to fail prematurely. Always handle by the base or with clean gloves.
Good tip. What's the other ignition method?
Direct spark ignition, or DSI. Think of a spark plug. It uses a high voltage, could be up to 5,000 volts, to create a spark across a gap, directly igniting the main burner gas.
Simpler, maybe?
Mechanically simpler, perhaps. Both are very common.
Okay, so the gas is lit electronically. How does the system know the flame is actually there and stable? The thermocouple is gone.
Modern systems use something called flame rectification.
Sounds technical. How does that work?
It's pretty neat, actually. The flame itself, the fire, can conduct electricity, but it acts like a diode. It lets current flow more easily in one direction than the other.
Really? A flame conducts electricity?
It does, due to the ionization of gases. The electronic control board sends a small AC voltage to a flame sensor rod that sits in the flame path. The flame rectifies this AC into a pulsing DC signal.
And the board looks for that specific DC signal.
Exactly. If it senses that tiny DC microamp current, it knows the flame is established and stable. If the flame goes out, the path is broken, The DC signal disappears, and the board shuts off the gas valve instantly. It's very fast and reliable.
Faster than a thermocouple cooling down.
Much faster, milliseconds.
Okay, so before ignition even happens, these modern systems go through a whole safety check sequence, starting with a blower.
Right, the combustion air blower, sometimes called an inducer fan. It serves a couple of purposes. First, it runs for a bit before ignition. That's the pre-purge.
Clearing out any leftover gas.
Precisely. Pushes any unburnt gas out of the combustion chamber and vents. Then, after the heating cycle ends, it runs again for a post-purge to clear out the remaining combustion products.
And the system needs proof that this blower is actually working, moving air.
Absolutely critical. That's the job of the combustion air proving switch, or CPS. It's usually a pressure switch.
A pressure switch. How does that prove airflow?
The blower creates a slight negative pressure draft. The switch senses this pressure difference. If the pressure changes correctly, the switch closes, telling the control board, yep, the blower is running and moving air as expected.
And if it doesn't close, maybe the vent is blocked or the blower failed.
Then the control board stops everything. It won't even try to ignite the gas. It assumes an unsafe condition like a blocked flue and locks out the system. It's a major safety interlock. If that switch fails, you get a no-heat call.
Makes sense. And there's one more mechanical safety, right? The rollout switch.
Yes, the rollout limit control. This is a safety device, usually a manual reset switch, located right near the burners.
What's it looking for?
It's looking for flames where they shouldn't be. If there's a blockage or a problem inside the heat exchanger, causing the flames to literally roll out of the front of the combustion chamber.
That sounds bad.
It is bad.
Yeah.
That switch senses the excessive heat from those errant flames and trips, cutting power. And because it's manual reset, a technician has to investigate why it tripped before the furnace can run again. It signals a serious problem.
Wow. Okay, so coordinating all of this, ignition, flame sensing, blowers, proving switches, limits, that's the job of the main brain.
The electronic control board, or ECB, yeah, it's the central processor.
Yeah.
It's replaced almost all the complex low-voltage relay logic you'd find in older systems.
It manages everything.
Pretty much. Ignition sequence, timing, monitoring all the safety inputs, controlling blower speeds for heating and cooling, interfacing with the thermostat, air conditioner, even things like humidifiers or HRVs.
But the configuration is critical.
Extremely. The source materials really emphasize this. You can't just swap boards randomly. The board has to be configured exactly for the specific furnace model. Its BTU rating, the type of gas, blower speeds. Getting it wrong isn't just inefficient, it can be dangerous, like explosion dangerous.
Yikes. Okay. Need the right board, set up the right way.
Non-negotiable.
All right, let's zoom out a bit. System integration. Building codes often require linking ventilation systems with the furnace, right? For makeup air.
Yes, that's a big one, especially with tighter modern homes. The National Building Code, for example. If you have powerful exhaust fans, like a big kitchen range hood or an HRV running on high, they can suck a lot of air out of the house,
Creating negative pressure.
which can cause problems like backdrafting chimneys or water heaters. So the code often requires these exhaust systems to be interlocked with the furnace's fan system.
So when the exhaust fan runs, the furnace fan also runs to pull in fresh makeup air.
That's the idea. But you hit an electrical code issue. The exhaust fan is usually 120 volts. The furnace fan control circuit is typically 24 volts, class 2.
And you can't mix those voltages in the same electrical box or raceway CE code rule.
Correct. So how do you make them talk to each other safely?
Good idea.
You need isolation. The standard method is to use a small, separate 120 volt to 24 volt transformer powered by the exhaust fan circuit. That 24 volt output then energizes a simple relay, just a coil and contacts.
Ah, and the relay contacts.
The relay's contacts are wired into the furnace's low voltage thermostat terminals, specifically across R, the 24V power, and G, the fan control.
So exhaust fan turns on, powers the little transformer, energizes the relay, closes the RG circuit on the furnace fan, turns on.
Bingo. A safe, code-compliant way to interlock the high-voltage exhaust system with the low-voltage furnace fan control, providing that necessary makeup air. Clever workaround.
Very neat. Okay, let's wrap this up with the core troubleshooting idea. When one of these complex systems doesn't work, what's the basic electrical approach?
It boils down to comparing input versus output across components. Voltage checks are key.
So if you check across a control device, switch, thermostat, limit, and you read the full source voltage.
That means the control device is open. It's stopping the flow of electricity. If it's supposed to be closed at that moment, then that device is likely your problem. It has voltage across it because it's breaking the circuit.
Okay. And what if the controls seem fine and you measure voltage across a load device like the gas valve coil or a motor?
If you measure the correct source voltage across the load, that means the electricity is getting to the load. The input is correct. But if the load isn't doing its job, the valve isn't opening, the motor isn't turning, then the load device itself is probably faulty. Correct input, no output.
Simple logic, input versus output. And there was a tip about weird voltage readings.
Yes. If you measure voltage somewhere in the circuit, and it's significantly less than the source voltage, not zero, but some odd fraction, treat it as zero for troubleshooting purposes.
Why?
Because it usually indicates there are multiple open points or high-resistance connections in the circuit somewhere, messing up the reading. Don't chase those weird fractional voltages. Find the primary open circuit first, the spot where you read the full source voltage across a component that should be closed.
Solid practical advice. Find the main break first.
Always.
Wow. We've really gone from the simplest heating element, that Joule effect, and that old, elegant millivolt thermocouple system.
All the way to these incredibly complex, sealed combustion Joule heat exchanger condensing furnaces hitting 98% efficiency. It's quite an evolution.
It really underscores that heating systems aren't just about fire and fans anymore. They are sophisticated electrical control circuits. Layers upon layers of safety logic managed by electronics based on physics like flame rectification and pressure sensing.
Absolutely. Governed by strict protocols to prevent things from going wrong.
So what this means for you, listening, is that you now kind of have the keys to the kingdom, understanding that sequence. Every click, every whir, it's part of a precise electrical gauntlet.
It is. And thinking about that journey, especially to the high-efficiency units, we learned they achieve that amazing efficiency by deliberately creating carbonic acid, a corrosive liquid.
Requiring expensive materials like stainless steel and careful drainage.
Right, which makes you wonder, what's next? How could heating tech maybe get to that ultra-high efficiency without relying on condensation and the corrosion it brings? Is there a way to capture heat differently?
And what about safety? Will we move beyond physical pressure switches, maybe towards more sophisticated electronic sensing for airflow and venting? What's the next safety challenge engineers need to solve?
Interesting questions. Definitely something to think about.
Indeed. Something to ponder the next time you hear that furnace kick on, especially that little pre-purge whir from the combustion blower. Thanks for taking this deep